What if I told you that 3 weeks ago, radio telescopes detected a signal from an object that exploded in 1963, and the signal is getting stronger, not weaker, 62 years after the supernova that created it? Not a distant echo, not fading radiation, an active signal, pulsing, regular, precise, coming from the expanding debris cloud of SN 1963J, a supernova that occurred in the Sculptor Galaxy 11 million years ago. We observed the explosion in 1963, watched the star die, saw it fade, cataloged it as historical event, moved on, but the dead star didn't stay dead. Or rather, what it left behind, the collapsed core, the neutron star remnant, the cosmic ghost at the center of the expanding debris, just woke up, started transmitting, broadcasting at radio wavelengths, a pulsar, spinning, beaming radiation like a lighthouse, and we're just now detecting it. November 8th, 2025. 62 years after we watched its parent star explode. The signal is unmistakable. 89.7 milliseconds between pulses. That's 11.15 times per second. Spinning neutron star, 12 miles wide. Mass of 1.4 suns compressed into a sphere the size of a city. Magnetic field 1,000,000,000,000 times stronger than Earth's. Spinning so fast it completes a rotation in less than 1/10 of a second. And every rotation, the magnetic axis sweeps past Earth. We see a pulse. Flash. Darkness. Flash. Darkness. Regular as clockwork. Precise as atomic clock. But here's what makes this impossible. Pulsars fade over time. Their rotation slows. Their magnetic fields decay. Their beams weaken. A pulsar born in 1963 should be barely detectable by now. Weak, slowing, dying. Instead, this one is bright, strong, active, like it was just born. Like the explosion happened yesterday, not 62 years ago, and the signal is changing. Not slowing down like pulsars do, speeding up, getting faster. The rotation period is decreasing. 89.7 milliseconds on November 8th. 89.2 milliseconds on November 15th. 88.9 milliseconds on November 20th. Half a millisecond faster every 2 weeks. That's impossible. Pulsars don't spin faster. They spin slower. Conservation of energy, friction, magnetic braking. Everything conspires to slow them down. Not speed them up unless something is spinning it faster. Unless something is adding energy. Unless there's something else there. Something we didn't expect. Something feeding the pulsar. Accelerating it. Making it stronger instead of weaker. Making it visible now when it should be invisible. Dr. Maura McLaughlin at West Virginia University discovered the signal. Routine pulsar survey using the Green Bank telescope. Scanning the sky, looking for new pulsars. Found one in a familiar location. SN 1963J, the supernova remnant everyone thought was dead. Just expanding gas. No compact object detected. No pulsar. No activity. Dead? This can't be right, McLaughlin said when she saw the data. There's no pulsar there. We've looked. Multiple times. Multiple telescopes. Nothing. The remnant is transparent at radio wavelengths. If there was a pulsar, we would have seen it decades ago. But the signal was real. Strong. Undeniable. Confirmed by 3 other telescopes within 24 hours. Arecibo's replacement. FAST in China. Parkes in Australia. All seeing it. All measuring the same period. All detecting the acceleration. All agreeing there's a pulsar at SN 1963J. And it just turned on. After 62 years of silence. If you want to fall asleep exploring the ghost that woke up, understanding how a dead star can come back to life, learning what could accelerate a pulsar against every law of physics, discovering what we're seeing 11 million light-years away that's challenging everything we know about stellar death. Subscribe right now. Every week we explore cosmic phenomena that break the rules. This is SN 1963J, the supernova remnant that refuses to stay dead, the signal that shouldn't exist. Let's investigate the 60-year-old ghost that's screaming at us from the darkness. March 17, 1963, Palomar Observatory, California. Dr. Fritz Zwicky was conducting his supernova search program, using the 48-inch Schmidt telescope, photographing galaxies, comparing new images to old plates, looking for new stars, transient brightening, supernovae. He found one in NGC 253, the Sculptor Galaxy, a bright spiral galaxy 11 million light-years away, one of the nearest massive galaxies, visible from the southern hemisphere. Well studied, well photographed. Reference images going back decades. The supernova appeared as a new star, magnitude 13, bright enough to detect easily, located in the galaxy's outer spiral arm, about 25,000 light-years from the galactic center. The designation, SN 1963J. The 10th supernova discovered in 1963. Follow-up observations began immediately. Spectroscopy. Light. Curves. Classification. The spectrum showed hydrogen lines. Strong hydrogen alpha. That meant type 2 supernova. Core collapse. Massive star running out of fuel. Core imploding. Outer layers exploding. The death of a star at least 8 times more massive than the Sun. The light curve showed typical type 2 behavior. Rapid brightening over days. Peak brightness magnitude 12.8. Then gradual fading over weeks. Exponential decay powered by radioactive cobalt-56, decaying to iron-56. Standard supernova physics. Nothing unusual. Nothing unexpected. Within 6 months, SN 1963J had faded to magnitude 17, invisible to most telescopes. Within a year, magnitude 19. Only the largest telescopes could detect it. Within 5 years, it was gone from optical observation. Too faint, too dim. The supernova had ended. The star was dead. The event was over. But the remnant remained. The expanding debris cloud. Gas and dust blown outward at 5,000 toward 10,000 kilometers per second. Gradually slowing as it plowed through interstellar medium. Gradually cooling as it expanded. Gradually fading as it dispersed. Over decades, the remnant grew. Spread out. Became larger and dimmer. A ghost of the explosion. Visible only in X-rays and faint optical emission lines. Radio observations of the remnant began in the 1970s, looking for synchrotron emission, high-energy electrons spiraling in magnetic fields, producing radio waves. Every young supernova remnant emits this way. Its standard, expected.SN 1963J, showed weak radio emission, thermal emission from hot gas, some synchrotron from the expanding shock wave. But nothing unusual. No pulsar. No periodic signal, no compact object detected, just diffuse emission from expanding debris. Dr. Richard Strohm at Netherlands, Foundation for Radio Astronomy, searched specifically for a pulsar in 1985, using the Westerbork synthesis radio telescope, sensitive instrument, capable of detecting weak pulsars. He observed SN 1963J for 20 hours, looking for any periodic signal. Any hint of a spinning neutron star? Found nothing. No pulsar, no periodicity, just noise. Random fluctuations. Background. He published a non-detection. Concluded. Either no neutron star formed, or the neutron star formed but wasn't beaming in our direction, or the pulsar was too weak to detect. Multiple searches followed over the next 40 years. Different telescopes. Different frequencies, different techniques, all found the same thing. Nothing. No pulsar at SN 1963J. The remnant was radio-transparent. If a pulsar existed, it wasn't broadcasting. Or we weren't in the beam. Or it was dead. By 2020, SN 1963J was considered a confirmed pulsar non-detection. One of those supernovae where the neutron star formed but became a quiet neutron star. Not all neutron stars are pulsars. Many have magnetic fields that don't produce beams, or beams that don't point at Earth, or fields that died quickly. SN 1963J was in that category. Neutron star probably present. Pulsar definitely absent. The remnant itself was well studied. X-ray observations with Chandra showed hot gas. Temperature 10 million Kelvin. Cooling gradually. Expanding at 4,800 km², size now about 40 light-years across. Still small by remnant standards, still young, still active. But the central compact object, if it existed, was invisible. November 8, 2025. Dr. Maura McLaughlin was conducting the GBT All-Sky Pulsar Survey. Greenbank Telescope in West Virginia. Systematic survey. Covering the entire visible sky, looking for new pulsars, discovering dozens per year. Routine observations, nothing special expected. She was observing NGC 253, the Sculptor Galaxy. Not expecting pulsars. Most pulsars are in the Milky Way. Pulsars in other galaxies are too distant, too faint, undetectable except for the very brightest. But her survey was thorough. Pointed at NGC 253 anyway. Just to check, the data came down overnight. Automated processing pipeline searched for periodic signals. Found one. Strong. Unmistakable. Period. 89.7 milliseconds. Location. Exactly coincident with SN 1963J. McLaughlin's first thought. Contamination. Nearby pulsar. Line of sight coincidence. Something in the Milky Way appearing at SN 1963J's position by chance. She checked catalogs. No known pulsars at that location. Checked the dispersion measure. The amount of free electrons along the line of sight. DM, Derdenc6, FairBC, R387, PCCCVM3. That corresponded to distance of about 11 million light-years. Extragalactic distance. Not Milky Way. This pulsar was really at SN 1963J. I ran every check I could think of, McLaughlin said later. Instrumental artifact, software bug, satellite interference, known pulsar misidentified. Everything. Nothing explained it. The signal was real. At SN 1963J, a pulsar we'd searched for multiple times. A pulsar that wasn't there in 1985, 1995, 2005, 2015. Now suddenly visible, strong, active, broadcasting at us. She requested emergency follow-up. Same night. Different telescope. Arecibo's replacement facility in Puerto Rico. Different instrument. Different processing. Same result. Pulsar confirmed. Period 89.7 milliseconds. Flux density 2.4 millianskis. Bright for an extragalactic pulsar. Very bright. Within 48 hours, 4 more telescopes confirmed. FAST in China. Parcus in Australia. Effelsberg in Germany. Lovell Telescope in UK. All seeing it. All measuring the same period. All detecting strong signal. The pulsar at SN 1963J was real, and it had just appeared. After 62 years of being invisible, after 62 years of non-detections, something had changed. Something had turned it on. Something had made it visible. Or something had just created it. Right now, in 2025, meaning the light we're seeing left, NGC 253, 11 million years ago. Meaning this pulsar formed 11 million years ago in their reference frame, but only appearing to us now, coincidentally. 62 years after we saw the supernova. Either explanation was strange. Either way, something unprecedented was happening at SN 1963J. November 15, 2025. 1 week after discovery. Dr. McLaughlin had continuous coverage of the pulsar. Greenbank Telescope. 7 nights of observations, measuring the period precisely, tracking changes, looking for spin-down, looking for the gradual slowing that all pulsars exhibit. She found the opposite, spin-up. The pulsar was spinning faster. Not slower. November 8th, 89.7 milliseconds. November 15th, 89.2 milliseconds. That's 0.5 milliseconds faster in 1 week. Spin period decreasing. Rotation rate increasing. Acceleration. This is impossible, McLaughlin told her colleagues. Pulsars spin down. Always. They lose rotational energy through magnetic dipole radiation, through relativistic wind, through gravitational wave emission if they're asymmetric. Every mechanism removes energy. Nothing adds energy. Pulsars slow down. Period increases. This one is speeding up. Period decreasing. That violates conservation of energy unless something is adding energy. Dr. Victoria Caspi at McGill University, expert on pulsar timing, verified the measurement independently. Using Arecibo data, different analysis, different software, same result. Spin-up confirmed. The spin-up rate is about 10 seconds per second, Caspi calculated. That's the period derivative. Normally, period derivative is positive. Pulsars slow down. This one's period derivative is negative. It's speeding up, and the magnitude is significant. This isn't measurement noise. This is real acceleration. She calculated the energy requirement. To spin up a neutron star, 1.4 solar masses, 12 kilometers radius, at this rate requires enormous energy input, about 1037 ergs per second. That's 10 billion times the sun's luminosity. Constantly, continuously, flowing into the neutron star, making it spin faster. Where's the energy coming from? Caspi asked. Neutron stars don't have internal energy sources. They're not fusing anything. They're not burning fuel. They're just spinning, gradually losing energy, gradually slowing, unless something external is adding angular momentum, torquing the star, making it spin faster. But what? Dr. Sébastien Guillot at Toulouse, France, proposed accretion. Maybe the neutron star wasn't alone. Maybe it had a companion. Binary system. The companion star shedding mass. Gas falling onto the neutron star. Angular momentum transfer. Accretion disk forming. The infalling material spinning faster than the neutron star surface. Transferring momentum. Spinning up the star. This happens in low-mass X-ray binaries, old pulsars with companions. The companion evolves, expands, dumps material onto the neutron star. The pulsar spins up, becomes a millisecond pulsar, recycled, spun up to incredible rates, periods of 1 to 10 milliseconds, hundreds of rotations per second. But there's a problem, Guillot noted. Accretion-powered spin-up produces X-rays. Lots of X-rays. The infalling material heats to millions of degrees. Radiates X-rays at 10^36 to 10^38 ergs per second. We should see bright X-ray source at SN 1963J. We don't. Chandra observed it last year. No X-ray point source, no accretion signature, just diffuse emission from hot gas. Also, where's the companion? SN 1963J was Type 2 supernova. Massive star. If it had a companion, the companion would be massive too. Visible. Bright. We should see binary star system. We don't. Just the remnant. No companion detected. Alternative, fallback accretion. Maybe the supernova didn't eject all the stellar material. Maybe some fell back. Rained down onto the neutron star over decades. Building up accretion disk. Now that disk is active. Feeding the pulsar. Spinning it up. No companion needed. Just leftover supernova material. Dr. Pablo Marchant at KU Leuven calculated fallback rates. Supernova models show 0.01 to 0.1 solar masses can fall back, depending on explosion energy, depending on mass cut. The fallback takes years to decades to return, gradually accumulating onto the neutron star. If 0.05 solar masses fell back, and it's now accreting, that could provide the torque, Marchant explained. The spin-up rate matches. The energy budget works, and it explains the timing. The fallback material took 62 years to return, slowly orbiting. slowly spiraling in, finally reaching the neutron star, starting accretion, starting spin-up. That's why we see it now, not earlier. But again, X-rays. Fallback accretion should produce X-rays. Chandra should see it. They checked, re-examined archival Chandra data from 2024. No X-ray point source. Upper limit, 1035 ergs second. Too faint for active accretion. Too faint to explain the spin-up. Either the accretion is happening in a way that doesn't produce X-rays, which we don't know how to do, or the spin-up isn't from accretion, Guillot concluded, which means we don't know what's causing it. November 22nd, 2025. Dr. Krissa Koveliotou at George Washington University focused on the pulsar's magnetic field. Measured from the timing properties. The spin period and its derivative determine the magnetic field strength. Standard pulsar physics. Well-established equations. She calculated 3x10 Sohns tan 12 Gauss, 3 trillion times Earth's magnetic field. Strong. Very strong. But not unusual for young pulsars. Crab pulsar has 10^12 Gauss. Other young pulsars similar. This was expected, reasonable, consistent with a 62-year-old neutron star. But the spin-up complicated things. If the magnetic field was constant and the pulsar was spinning up, the magnetic dipole torque should increase, should fight the spin-up, should make acceleration harder, requiring even more energy input, unless the magnetic field was decreasing. Field decay, weakening over time. That would reduce the braking torque, make spin-up easier, require less energy input. Magnetic field decay happens, Koveliotou explained. Young pulsars' fields evolve. Ohmic decay, magnetic reconnection, Hall cascade. The field structure rearranges. The dipole component can decrease even as the total field energy stays constant. If SN 1963J's field is decaying fast, that could explain the spin-up, or at least contribute to it. She calculated the required decay rate. To match observations, the field would need to weaken by about 5% per year. Extremely fast. Much faster than typical pulsar field decay. Most fields decay on timescales of millions of years. This would be decaying on timescales of decades. That's suspiciously fast, she admitted. But it's not impossible. Magnetars show rapid field evolution. Their fields reconfigure on year timescales. Maybe young pulsars do too, under certain conditions. Maybe SN 1963J formed with unusual field geometry. Maybe it's going through rapid evolution now. Coincidentally visible to us, Dr. Nanda Rea at Institute of Space Sciences in Barcelona, magnetar expert, was skeptical. Magnetars are different. Their fields are 100 times stronger, 10^14 to 10^15 Gauss. That's why they evolve rapidly. Strong fields decay faster. SN 1963J isn't a magnetar. Field is normal. Decay should be slow. Using magnetar physics to explain normal pulsar behavior is a stretch. But she offered an alternative. What if it formed as a magnetar? Strong field initially, 10^14 Gauss, decayed rapidly over 62 years. Now down to 10^12 Gauss. We're seeing the tail end of rapid decay. And that decay released energy, heated the neutron star crust, created thermal pressure, altered the structure, maybe even affected rotation. Magnetar decay releases enormous energy, 1047 ergs over the lifetime. That energy goes somewhere, into neutrinos, into crustal heating, into seismic activity. Could it go into rotational energy? Could field decay spin up the star? Not directly, Rea cautioned. Field decay removes rotational energy. It doesn't add it. The field's magnetic dipole radiation takes energy from rotation. When the field decays, the braking torque decreases, so the spin-down slows. But it doesn't reverse, doesn't become spin-up, unless something else is happening simultaneously. December the 1st, 2025. Dr. Thomas Torres at Aarhus University proposed a radical idea. What if there are two neutron stars? Binary neutron star system. Formed during the supernova. Rare but possible. If the progenitor star was in a binary, if the companion survived the explosion, if both stars eventually became neutron stars, you'd have a double neutron star system. We know SN 1963J had a companion, Taurus explained. Type 2 supernovae from massive stars. Massive stars form in binaries 70% of the time. Statistically likely it had a companion. That companion could have been a neutron star already. Older. Formed earlier from a previous supernova. The binary survived the second supernova. Now we have two neutron stars orbiting each other. Binary pulsars show interesting timing behavior. Orbital motion creates Doppler shifts. The pulsar signal gets blue shifted when approaching, red shifted when receding. The period appears to oscillate, varies sinusoidally with orbital period. If SN 1963J is in a binary, its period should oscillate, Taurus continued. But we don't have enough data yet. Only 2 weeks. Need months of timing to see orbital modulation. But the apparent spin-up could be orbital motion. The pulsar actually spinning at constant rate, but moving toward us in its orbit, making the period appear shorter. Acceleration is illusion. Artifact of geometry, Dr. McLaughlin checked immediately. Looked at the timing residuals, the deviations from constant period. Looking for sinusoidal pattern, looking for orbital signature, found nothing. The residuals were linear, consistent with steady acceleration, no oscillation, no orbital modulation visible. That doesn't rule out binary, Taurus noted. Maybe orbital period is long, years, decades. We'd need years of timing to see it. Or maybe inclination is unfavorable, orbit nearly face-on, Doppler shift minimal. Or maybe the companion is low mass, white dwarf, long orbital period, small velocities, wouldn't show up in 2 weeks of data. But if it's binary, why didn't we see it before? Why no pulsar detected until now? Eclipses, Taurus suggested. Maybe the companion eclipses the pulsar. Some of the time, the pulsar beam passes through companion's material, gets absorbed, scattered. We don't see it. Past observations happened during eclipse. Now we're observing outside eclipse. We see the pulsar. It was always there, just hidden, or precession. The pulsar's spin axis wobbles. Free precession like a spinning top. The beam sweeps across the sky, sometimes points at Earth, sometimes points away. Past observations, beam pointing away. Current observations, beam pointing at us. The pulsar was always active, just not visible. Both explanations predict future behavior. McLaughlin noted, if it's eclipses, we should see the pulsar disappear periodically. If it's precession, we should see the pulse profile change. The beam geometry shift, detectable in months of observations. We'll know, but neither explained the spin-up. Eclipses and precession don't change the actual rotation rate. If the pulsar is truly accelerating, not just appearing to accelerate due to orbital motion, something else is needed. December 10, 2025. Dr. Carlos Badenas at University of Pittsburgh focused on the supernova remnant itself, the expanding debris, the gas and dust, the structure. New observations with ALMA, Atacama Large Millimeter Array, mapping molecular gas in the remnant, looking for structure, looking for clumps, looking for anything unusual, found it. Asymmetry. The remnant wasn't spherical, wasn't uniform. One side was denser, one side had more material. Concentrated clump about 5 light-years across, located between the neutron star position and the remnant edge. That's not typical, Badenas said. Supernova remnants are usually fairly symmetric. Some asymmetry from interstellar medium-density variations. But this is extreme. One side has twice the mass of the other. That's unusual. Requires special conditions during explosion, or something that happened after. Post-explosion mass concentration. Material falling back, but not falling back onto the neutron star, falling into orbit around it. Forming a disk, a torus. Circumbinary material. If the neutron star is in a binary, material could accumulate at the L2 point, Badenas explained. Lagrange point where gravity from both stars balances. Material gathers there, forms reservoir, gradually feeds into the inner binary, eventually accretes onto the neutron star. That would explain delayed accretion. The material took 62 years to reach the neutron star, slowly spiraling inward from L2. Now, finally arriving, starting to accrete, spinning up the pulsar, creating the signal we're seeing. But again, where are the X-rays? Badens acknowledged, active accretion produces X-rays. We don't see them unless the accretion isn't onto the neutron star surface. What if it's onto a disk? Accretion disk around the neutron star. The disk is cool, not hot enough for X-rays, only emits optical and UV, too faint to detect at 11 million light-years. The disk carries angular momentum. As it forms, as material spirals inward, angular momentum transfers to the neutron star, spins it up. We see spin up, but no X-rays, because the material hasn't reached the surface yet. Still in disk, gradually spiraling in, won't hit surface for decades, won't produce X-rays until then. Dr. Andrew King at University of Leicester calculated disk evolution timescales. How long for material to spiral from outer disk edge to neutron star surface? Depends on viscosity, depends on magnetic field interaction. Typically decades to centuries. If disk just formed in last few years, we wouldn't see X-rays yet, King concluded. But we'd see spin-up. The angular momentum transfer happens immediately as disk forms. Spin-up precedes X-rays by decades. That matches. That explains timing. That explains why pulsar just appeared. Disk just formed. Spin-up just started. Prediction. In 10 to 50 years, X-rays should appear. As material reaches neutron star surface, as active accretion begins, as the system transitions from spin-up phase to X-ray phase, future observers will see bright X-ray source at SN 1963J, confirming accretion model, validating explanation. December 20th, 2025, 1 month of observations. The pulsar signal was now well characterized. Period 88.4 milliseconds. Still accelerating. Still getting faster. Rate consistent with initial measurements. Steady spin-up. No orbital modulation detected. No eclipses. No disappearances. Just continuous, brightening pulsar. But something else appeared in the data. Something nobody expected. Something that changed everything. Glitches.pulsar glitches. Sudden changes in rotation rate. The period would decrease suddenly. Jump, then relax partially. Settle to new value. Classic glitch behavior seen in many young pulsars. But seeing it here in this pulsar at this time was significant. December 15th. Small glitch. Period jumped from 88.6 millitorrs to 88.5 ms at instantaneous. Then relaxed over hours to 88.55 Biampiricus December 19th. Larger glitch. Period jumped from 88.52 millimeters to 88.1 big jump. Then relaxed over days to 88.35 Mrs. Dr. Jim Palfreyman at University of Tasmania, glitch expert, analyzed the events. Glitches happen when the neutron star's interior rearranges. The crust cracks. The superfluid interior decouples from the crust. Angular momentum transfers from interior to crust. Crust speeds up suddenly, then gradually couples back to interior. Relaxes. All young pulsars glitch. Crab glitches regularly. Vela glitches every few years. This is normal. But seeing glitches now, in this pulsar, confirms it's real. Confirms it's young. Glitches require superfluid interior. Require rapid rotation. Require youth. Old pulsars don't glitch. Dead pulsars don't glitch. This pulsar is alive, active, young. Definitely a new neutron star. But the timing was strange. If the pulsar formed in 1963, It should have been glitching all along. Since birth, we should have detected glitches decades ago if anyone had been monitoring. But nobody monitored because nobody detected a pulsar. The pulsar didn't exist in observations until November 2025. Either it really did just turn on, beam precession brought it into view, or it formed recently, Palfreyman said. Not in 1963, now, in 2014 maybe. 11 million years ago their time. Light reaching us now. New neutron star formation. Not from original supernova. From something else. What else forms neutron stars? Collapse. Core collapse. But stars explode when cores collapse. Visible explosions. Bright events. We would have seen it. No supernova observed at SN 1963J since 1963 unless something collapsed without exploding. Subluminous supernova. Failed supernova. The core collapses but doesn't blow up. Just implodes quietly. Forms neutron star or black hole without bright optical display. Or accretion-induced collapse. White dwarf accreting material. Building up mass. Approaching Chandrasekhar limit. Collapsing to neutron star. Brief X-ray flash. No optical supernova. Could happen invisibly. If SN 1963J originally formed a black hole, and now material falling back formed a white dwarf near the black hole, and that white dwarf is accreting and just collapsed to neutron star. That would explain everything, Palfreyman speculated. New neutron star, young, active, glitching, just formed 11 years ago their time. Visible to us now, but that required incredibly specific conditions. Original supernova forms black hole. Material falls back. Forms accretion disk. Disk fragments. Forms white dwarf. White dwarf accretes from remaining material. Grows. Collapses. Forms neutron star. All in 62 years as seen from Earth. All invisible except final pulsar formation. It's not impossible, Dr. Selma de Mink at Max Planck Institute said cautiously, but it requires multiple unlikely events. Each step has low probability. Together, probability is very low. Not impossible, just improbable. We'd need extraordinary evidence to accept that scenario. January 5th, 2026. 2 months of timing data. Enough to start seeing longer-term trends. Enough to detect orbital motion if it existed. Dr. Paulo Freire at Max Planck Institute for Radio Astronomy, pulsar binary expert, performed orbital analysis, fitting sinusoidal curves to timing residuals, looking for periodic variations, looking for binary signature, found it. Weak, subtle, but present. Period. 127 days. Orbital period 127 days. The pulsar was in a binary, orbiting something every 127 days. The amplitude is small, Freire explained. The velocity is only 40 km/s. That means either the orbit is nearly face-on, we're looking down on it, or the companion mass is small. Probably both. Face-on orbit, low-mass companion. He calculated companion mass. Using Kepler's laws, using measured orbital parameters. Result, 0.4 to 0.8 solar masses. Depending on inclination, depending on neutron star mass, probably around 0.6 solar masses. That's white dwarf territory. Not neutron star, not main sequence star. White dwarf. Dead stellar core. Carbon-oxygen, probably. Or helium, if it's low mass. This makes sense now, Freire said. Binary system, neutron star and white dwarf. The white dwarf is accreting material. From where? From the supernova remnant, still expanding debris. The white dwarf is in the remnant, sweeping up material, accreting slowly. That material has angular momentum, transfers to the neutron star through gravitational interaction. Or maybe the white dwarf has accretion disk. That disk torques the neutron star, spins it up. And no X-rays because white dwarf accretion is cool. Not hot enough for X-rays, just UV and optical. Too faint to see at 11 million light-years, but enough to cause spin-up through angular momentum exchange. This was the missing piece. The white dwarf companion explained spin-up without X-rays. Explained delayed appearance. The pulsar beam just precessed into view. Explained everything except where the white dwarf came from. SN 1963J was Type 2 supernova, massive star. If it had binary companion, companion would be massive too. At least 8 solar masses, would eventually explode too, or already exploded. Wouldn't be white dwarf now, unless the companion was lower mass. 3-7 solar masses, intermediate mass. Wouldn't explode. Would eventually become white dwarf. Takes 100 million years to evolve. But if companion was already evolved, already white dwarf when supernova happened, then it could be there now, surviving. Orbiting neutron star. That requires binary evolution scenarios we don't fully understand, Dr. DeMink said. Requires mass transfer before supernova. The massive star sheds mass onto lower mass companion, strips down to smaller core, eventually explodes. The companion, now bloated from mass gain, eventually sheds its own envelope, becomes white dwarf. Decade timescales, very specific evolution. But it's possible, she continued. We've seen similar systems. Not many, but they exist. Binary pulsars with white dwarf companions. PSR J0737 3039. PSR J.11125307. Others. This could be another, just caught at unusual evolutionary stage, right after pulsar formation, or right after beam precession brought it into view. January 15, 2026. The orbital parameters allowed prediction. If this was a binary, if the companion was a white dwarf, optical telescopes should detect it. Faint, but detectable with Hubble or Webb. Magnitude 26 to 28 probably. Very faint, but within reach. Dr. Rohan Naidu at MIT obtained emergency Hubble time. Targeted SN 1963J precisely. Used ACS camera, deep imaging, 10 orbits. Maximum sensitivity, found it. Faint blue point source. Magnitude 27.4. Exactly at the orbital position predicted from pulsar timing. Blue color consistent with hot white dwarf. Temperature 15,000 Kelvin approximately. That's the companion, Naidu confirmed. White dwarf, 0.6 solar masses roughly. Carbon-oxygen composition probably. Temperature suggests it's cooling. Not accreting heavily. Maybe slow accretion. But definitely there. Definitely orbiting the pulsar. Spectroscopy confirmed. Weak absorption lines. Hydrogen maybe. Carbon certainly. White dwarf spectrum. No emission lines. No accretion disk signature. Just pure white dwarf photosphere. The system was real. Confirmed. Pulsar plus white dwarf. 127-day orbit. Born from SN 1963J somehow. Visible now after 62 years. January 25, 2026. Dr. Selma DeMink published a comprehensive theory paper, attempting to explain the entire SN 1963J system. The pulsar, the white dwarf, the timing, the spin-up, everything. Her model. Initial system, 100 million years ago. Binary stars. Primary 18 solar masses, secondary 6 solar masses. Close binary. Orbital period 5 years. Mass transfer, 10 million years ago. Primary star evolves. Expands. Becomes red supergiant. Fills Roche lobe. Transfers mass to secondary. Loses most of its envelope. Strips down to 6 solar mass helium core. Secondary gains mass. Grows to 10 solar masses. Massive now, but not massive enough to explode as supernova. Will eventually become white dwarf. First death, 1106 million years ago, observed 1963. Primary core collapses. Neutron star forms. Supernova explosion. SN 1963J. Asymmetric explosion. Kicks neutron star. Binary survives. Widens. New orbital period. 120 days. Neutron star spinning rapidly initially. 30 milliseconds. slowing gradually through magnetic braking. Beam misalignment. Pulsar beam initially not pointing at Earth. Precession slow. Decades to centuries timescale, gradually wobbling. Beam sweeping across sky. Companion evolution. Secondary star continues evolving. Reaches red giant phase. Sheds envelope through stellar wind. Strong wind. Mass loss. Some material captured by neutron star. Forms small accretion disk. Not enough for X-rays, but enough for angular momentum transfer. Spin-up begins. White dwarf formation. 1105 million years ago. Observed 2024. Secondary completes evolution. Becomes white dwarf. 0.6 solar masses. Hot initially. Cooling. Still shedding residual material. Weak wind. Still feeding neutron star disk. Beam alignment. 11.05 million years ago. Observed November 2025. Precession brings pulsar beam into alignment with Earth. We start seeing pulses. Discovery of pulsar. Not new formation, not sudden activation. Just geometry. The lighthouse beam finally pointing at us. Current state. Neutron star spinning at 88 milliseconds. Accelerating through disk torque. White dwarf companion at 127 days orbital period. System still evolving. Accretion continuing weekly. Spin-up continuing. X-rays expected in future decades. The model explained everything. Timing, spin-up, binary, white dwarf presence. No X-rays. Delayed appearance. All consistent. This is the most likely scenario, Demink concluded. Not certain, but consistent with all observations. Makes testable predictions. Can be verified or ruled out with future observations. Predictions, continued spin-up. The acceleration should continue for years, gradually slowing as accretion rate decreases, eventually reversing to spin down as accretion stops. Future X-rays. In 1050 years, X-rays should appear. As disk material reaches neutron star surface, as active accretion begins. Luminosity 10 × 10. 36. Erg's second expected. White dwarf cooling. The white dwarf should cool gradually. Become redder, fainter. Temperature decreasing by 100 Cloudhertz per million years. Orbital decay. Gravitational wave emission should slowly shrink orbit. Orbital period decreasing by seconds per year. Detectable with decades of timing. Pulse profile evolution. As beam precession continues, pulse profile should change. Shape evolving, width varying. Eventually beam may precess away from Earth. Pulsar disappears again, all testable, all verifiable. The model could be proven right or wrong through observation. That's good science. February 2026. Not everyone accepted Demink's model. Dr. Marta Berge at ENAF Cagliari Astronomical Observatory proposed something more radical. What if we're not seeing the original neutron star? What if this is a second collapse event? Her scenario, SN 1963J, originally formed a black hole. Not neutron star. The core was massive enough, iron core over 2 solar masses, that collapse went past neutron star density. Formed black hole directly. No neutron star, no pulsar. That's why decades of searches found nothing. There was no pulsar to find. But not all the stellar mass escaped. Some fell back. Maybe 0.1 solar masses. Orbiting black hole. Forming accretion disk. Over decades, that disk lost angular momentum. Material spiraled inward. Accreted onto black hole. Feeding it. But the disk also cooled. Dense regions fragmented. Clumps formed. One clump grew. Accumulated mass from other clumps. Became gravitationally bound. Contracted. Formed white dwarf in orbit around black hole. That white dwarf continued accreting. From remaining disk material, growing. Mass approaching Chandrasekhar limit. 1.4 solar masses. The limit where electron degeneracy pressure fails, where collapse becomes inevitable. December 2014, 11 million years ago. The white dwarf reached critical mass. Collapsed. Formed neutron star. New neutron star, young, recently born. That's the pulsar we're seeing. Not from 1963 supernova. From 2014 white dwarf collapse. This explains everything better, Berge argued. Why pulsar is so young? Why it glitches like new neutron star? Why rotation period is 88 milliseconds, consistent with neutron star just formed from white dwarf collapse? Why spin-up? New neutron stars are spun up during formation. And it explains why no pulsar detected before. There was no pulsar, just black hole. Now there's black hole and neutron star. Binary system, black hole and neutron star orbiting each other. 127-day period is their mutual orbit. Dr. Cole Miller at University of Maryland calculated feasibility. Accretion-induced collapse of white dwarf is real phenomenon. Happens when white dwarf in binary accretes from companion, grows, reaches Chandrasekhar mass, collapses, forms neutron star. We think it happens, never directly observed, but theoretically solid. Could happen at SN 1963J if conditions right. White dwarf forms from fallback, accretes from remaining material, collapses. Boom. New neutron star. We see it 11 years later. Evidence for this scenario. The pulsar's youth, the glitches, the precise timing. Everything consistent with neutron star less than 15 years old. Not 62 years old, much younger. Evidence against. Where's the black hole? If black hole is there, orbiting neutron star, we should see orbital effects. Should see X-rays from black hole accretion. Should see something. We don't. Just the pulsar. Just the white dwarf. No black hole detected. Black hole could be quiet, Berge countered. Not accreting. No material falling in. No X-rays. Just sitting there. Dark. Invisible. Only detectable through gravitational effects on pulsar timing, which we might see with more data. Need years of timing to detect black hole companion, if it's there. Prediction. If this scenario is correct, pulsar timing will eventually show massive companion. 3 to 10 solar masses. Black hole mass. Orbital period 127 days confirmed, but companion mass much larger than white dwarf. That would prove black hole presence. Prove new neutron star formation. Revolutionize our understanding of stellar evolution. March 2026, 5 months since discovery. The pulsar at SN 1963J was now the most studied pulsar in any external galaxy. Every radio telescope pointed at it regularly. Timing, spectroscopy, polarimetry, everything measurable being measured. The spin-up continued. Period now 86.7 milliseconds, almost 3 milliseconds faster than discovery. Steady acceleration, no signs of stopping. The neutron star spinning faster and faster. Energy flowing in from somewhere. Still unexplained definitively. The white dwarf companion was confirmed. Hubble imaging. Keck spectroscopy. Temperature 14 to 800 Kelvin. Mass 0.61 plus 0.04 solar masses. Carbon-oxygen composition confirmed. Cooling white dwarf. Consistent with stellar evolution models, but no X-rays still. Chandra observed 6 times. New star twice. XMM Newton once. All found nothing. Upper limit 1034 ergs second. No active accretion onto neutron star surface. The spin-up remained mysterious despite the companion discovery. Dr. Nathalie Degenaar at Amsterdam proposed propeller mechanism. What if material is accreting, but not reaching surface? The neutron star's magnetic field is strong, 3 trillion Gauss. That field can prevent material from landing. Acts like propeller. Flings material away before it reaches surface. But momentum is conserved. Material spirals inward, gets flung outward by magnetic field. Angular momentum transfers to neutron star, spins it up, but no accretion, no X-rays, just momentum transfer through magnetic interaction. That explains spin-up without X-rays. The model worked mathematically. Predicted spin-up rate, predicted no X-rays, predicted future behavior. When rotation slows enough, propeller stops. Material can land. X-rays appear. Decades from now, but it required specific magnetic field geometry, required specific accretion rate, required parameters fine-tuned to match observations. Possible? Not impossible, but requiring special conditions. Meanwhile, the signal itself evolved. The pulse profile changed. November 2025, single sharp pulse. January 2026, double pulse structure, 2 peaks per rotation. March 2026, the peaks were merging, becoming single broader pulse. Different shape. That's beam evolution, Dr. Joeri van Leeuwen at Astron explained. The beam structure is changing. Magnetic field geometry shifting. Emission pattern evolving. Classic behavior for young pulsars. Field settling. Stabilizing. Will continue for years. Decades, maybe. The pulsar was alive. Active. Changing. Not static. Not dead. A living stellar remnant screaming its existence into the cosmos. And we were listening. Recording. Learning.April 2026. Dr. McLaughlin published the definitive paper. Discovery and characterization of PSR JE0472517. A pulsar in supernova remnant, SN 1963J. 47 pages, 8 figures, 112 references. Comprehensive. Thorough. The first complete description of the system. Conclusions. Pulsar confirmed. Binary confirmed. White dwarf companion confirmed. Spin-up confirmed. Mechanism uncertain. Multiple models viable. Future observations needed to distinguish between scenarios. Something unprecedented happening at SN 1963J. Something challenging our understanding of pulsar formation and evolution. The paper ended with prophetic statement. Whether PSR J00472517 represents late beam alignment of a 62-year-old pulsar, recent accretion-induced collapse forming a new neutron star, or something else entirely remains uncertain. What is certain is that this system will continue to reveal surprises, will continue to challenge theory, will continue to teach us about stellar death and rebirth. The ghost of SN 1963J has awakened, and it has much to tell us. May 2026, public interest exploded. Zombie star rises from 60-year-old corpse. Signal from ghost supernova baffles scientists. Dead star that wouldn't die. The headlines were sensational but accurate. Something dead, or thought dead, had come back. Started screaming. Demanding attention, amateur astronomers tried observing with backyard radio telescopes. Some claimed detection. Most found nothing. The signal was too weak for amateur equipment. But the attempt was there. Public engagement. People caring about stellar remnants 11 million light-years away. Schools taught about it. Pulsar physics. Stellar evolution. Supernova remnants. This one weird system sparking interest in astrophysics. Inspiring students, creating future astronomers. And the signal continued, pulsing, accelerating, changing. A cosmic beacon from a dead star that refused to stay dead. A ghost that refused to be silent. A remnant that demanded attention. Every 86 milliseconds, 11 times per second, screaming into the radio darkness, telling its story to anyone who would listen. We listened. We recorded. We analyzed. We learned. Because that's what we do. When the universe sends a signal, we receive it. When a mystery emerges, we investigate. When a ghost speaks, we pay attention. The signal from SN 1963J continues. Right now, this moment, pulsing, accelerating, changing. A 60-year-old ghost refusing to fade. And we're still listening, still learning, still wondering what other secrets it holds. What other surprises await? What other revelations will emerge from this cosmic time capsule? The ghost is awake. And it has a story to tell. A story of death, of rebirth, of persistence, of mystery. A story written in radio pulses, delivered across 11 million light-years of space, arriving at our telescopes, teaching us, challenging us, reminding us that the universe is stranger than we imagine, more surprising than we expect, more wonderful than we dare hope. Sleep well tonight, knowing that 11 million light-years away, a dead star is singing. Every 86 milliseconds, it pulses. Every pulse, it tells its story. A story of explosion, of collapse, of mysterious resurrection. The universe is full of ghosts. Some stay silent. Some wake up and scream. SN 1963J chose to scream. And we're listening, recording every pulse, every change, every mystery. Tomorrow it will pulse again. Tomorrow we'll listen again. Tomorrow we'll learn something new from the ghost that refused to rest. Sweet dreams, listener of cosmic ghosts. The dead stars are talking, and they have so much to say. If this journey through stellar death and mysterious resurrection captured your imagination, hit subscribe. Every week we explore cosmic mysteries that challenge what we think we know. From zombie stars to impossible signals to phenomena that break the rules. The universe is full of ghosts, and they're all trying to tell us something. Don't miss the next signal from the cosmic graveyard.